So in this video lesson, we're going to cover endothermic and exothermic reactions and looking at reactions, chemical reactions, in a different way than we used to, and kind of focusing on the energy of those reactions now instead of just what the reaction is and what's actually taking place, but actually what's happening with the energy in these reactions. So make sure that if you're sitting at your computer now, you need to make sure you have something to write with, and you have the blue sheet that I gave you in class that has kind of some of the missing blanks and that you'll fill in as the video plays. Then you also use that information to answer the questions later in the video lesson. You're sitting by the campfire on a nice cool summer night, whether it's in your backyard, over at Allen Creek, or somewhere else, maybe on the beach with your family on vacation. Have you ever stopped to think why the fire burns and why you feel that heat and the chemical reaction that's taking place? Well, that's what we're going to focus on. Where does the fire get that energy? Why does it keep burning? It's going to kind of be the focus of this and what type of reactions we see. We've classified chemical reactions before. We're going to classify them a little further in terms of energy. Now, learning goals for today. Kind of this lesson here, this quick lesson. I want you to be able to determine whether a chemical reaction is endothermic or exothermic. I want you to be able to draw energy bar charts for a chemical reaction. And then I also want you to be able to draw the chemical potential energy curve for a chemical reaction. Now, first off, we're going to go kind of back to the law of conservation of energy. We've talked about this a little bit earlier, but just kind of to refresh that idea, you've heard it before in physical science. We're going to talk about it a little more closely as far as chemical reactions go. But just remember that energy cannot be created or destroyed. It is only transferred between objects and systems. So we don't ever see a net increase in the amount of energy we have. We just see energy being transferred through different systems, through different objects, which is why we see energy changes. Now, before, we kind of ignored chemical energy on our bar charts. But now we're going to kind of focus in on that and what really is going on during chemical reactions. Before, we were just talking about the energy kind of within different substances, just water or just some other substance, and not really what a chemical reaction. Nothing was changing, form. We just had phase changes and things like and temperature changes. But now we're really going to look at a chemical reaction. And chemical energy is energy due to the attractions of atoms within molecules. We commonly refer to those attractions as chemical bonds, and those bonds store energy within the molecules. We talked a little about that during the first semester, but now we're really going to focus in on those chemical bonds and the energy that is released or brought into the system when those bonds form or when they break. Now you can see that was a pretty intense chemical reaction, and we're going to start classifying our types of reactions now. Now the chemical reaction that we just saw with a very reactive metal like sodium or lithium, we're going to assume it was sodium, with water is referred to as an exothermic reaction. And in an exothermic reaction, the chemical energy in the bonds of our reactant, so what we start with, is transferred to the thermal energy account, and then it's released as heat. We feel the mixture getting hot, or we see that big flame, and we see that energy is transferred from one storage to the other. Now, in this case, when we first start, we have our metal just kind of sitting there on the table. We have water. They're at room temperature. There's a little bit of thermal energy, but not a whole lot that is going to really concern us. So we kind of put 2 bars in our bar chart. Now, the chemical energy, so the energy stored within the bonds, in the metal and in the water there's a lot of energy stored there. So we're going to show that with a lot more bars. So we're going to use 4 bars in this case. Now, when we bring those 2 substances together, we see the thermal energy increases significantly because we feel that heat. It feels hot. The reaction feels hot. We can see that with the heat and feel that with the heat coming off of the flame. Now, that energy that we transferred into the thermal are new molecules that we formed. So assuming it was sodium, we formed sodium hydroxide and hydrogen. There's not as much energy stored in those bonds in our products or the stuff that we made. So we see that as, our chemical energy has decreased as we move from the reactants to the products. And but you can still see that the law of conservation of energy still applies, because I still have 6 bars over here in my reactants graph, and I still have 6 bars over here in my products. I've just transferred that energy kind of differently within my system. Now, some key things about exothermic reactions. That it's going to feel hot to the touch because there's an increase in thermal energy. So if it's in a container, like if we did that experiment in a container, if we felt the container would feel really hot because we increased the amount of thermal energy in the system. The products have a lower chemical energy than the reactants, which we see in the bar chart. We see that the chemical energy here is a lot higher than it is over here with the products. So the products have a lower chemical energy. Now, also the energy, as far as when we write in a chemical equation, we're going to start writing chemical equations to show where the heater energy is. And in this case, the energy is going to show up as a product in our equation. So like I said, we reacted sodium with water right here to form sodium hydroxide and hydrogen gas. But then it releases heat and energy, so that becomes one of my products. I release heat and energy, and that's going to show up in my chemical equation. So some of the key things about an exothermic reaction. Easiest way to tell, you react 2 substances. Does the vessel or the container that you perform that chemical reaction, does it feel hot? And then we can use some other things to kind of figure out what type of reaction. So one thing we're going to kind of add now as we talk about endothermic and exothermic reactions is a chemical energy, or just an energy diagram. It's a little different than a bar chart, and we'll look at it a lot more closely once we kind of start talking a little more about the reactions. But on this graph, we just have chemical energy here, so energy kind of that's stored within the bonds of the molecules. And then down here, this is just represents reaction progress. You can think about that as time as well, but just as the reaction goes on, what happens to the energy. So when we look at an exothermic reaction, our reactants are going to have a lot of energy initially. So we can label this, and I'm going to label this just R for reactants. So they have some kind of set amount of stored energy. So looking at this area here. Now, we talked about in an exothermic reaction, the products have less chemical energy than the reactants do. They become more stable that way. So we kind of get a graph that would, hang on, let me redo that. Let's use purple. That would look kind of something like this. So where we get this reaction that takes place over time, and then we get our products down here at the bottom, where they're going to have now less energy because they're obviously lower on the graph over here than the reactants were. So the products are going to have a lot less energy. Now, this kind of hump here to get over, obviously it goes up and then comes back down. This area here, we call this the activation energy. So each reaction needs energy to kind of acquire some energy for this reaction even to take place. This part of the graph could be a whole video lesson in and of itself, so we're not going to focus on that a whole lot right now. Just knowing that the reactants have a lot more chemical energy than the products do in an exothermic reaction. And this is what all of our kind of graphs would look like with variances in how much energy. But the main shape looks like this. Now this video is going to help us with our next type of chemical reaction. Right in this video, what you see here is a mixture of iron, and solid sulfur. Now, what's going to happen is there's going to be kind of a heated glass rod that's going to come in and kind of help this reaction happen. It just does. We mix these two together. They're not going to react. We need some heat. We need some energy to make this reaction go. And we'll focus on that part of the kind of chemical reaction later. Right now, we're just kind of focusing on what happens to the system once the chemical reaction is actually occurring. So we're going to go ahead and watch this video here. There's some cool tango music. So we light it. We kind of see that the iron and sulfur will start to glow a little. And now they're reacting. So the flame's kind of gone. There's a little bit left. But they're reacting to form a new substance. So we now have solid iron sulfide that's now been created from this reaction. So that reaction of iron and sulfur is referred to as an endothermic reaction, where the thermal energy is absorbed into the system from that glass rod, because that glass rod was really hot, so the iron and the sulfur absorb that thermal energy or transfer it into the system, and they get really hot, but then that energy is transferred to chemical energy as the iron sulfide is created and brought together. So the iron and the sulfur atoms are brought together to form iron sulfide. And they're going to store a lot more chemical energy than the iron and the sulfur themselves. So here, the thermal energy is really high to start. So we have to bring that glass rod in. We have to have some heat or some energy to make this reaction happen. What I do not want you to assume, though, just because there was a flame there, that doesn't mean it's exothermic. That's just kind of the ignition of the reaction itself, and that's some of these reactions, when they're endothermic, will just kind of happen naturally. But this time, we need to add some heat and energy that's going to make the reaction happen. So we have a lot of thermal energy to start. There's not a lot of chemical energy, though, stored in our substances. There's a little bit stored, but not a whole lot, because we just have solid iron and solid sulfur. But once the reaction actually starts to take place, once we've added this heat and added this thermal energy, the chemical energy is going to increase a lot, because these new molecules that we're forming are storing a lot of energy in their bonds, in their chemical bonds. So that iron sulfide has a lot more energy than the iron and sulfur did itself. And then as that happens, the iron sulfide is going to cool down, and all of that thermal energy we kind of transferred into our system is going to decrease, and we transferred it over to our chemical energy. But again, if you look, we still have 6 bars here and 6 bars over here. Except now our chemical energy increased from reactants to products, and our thermal energy decreased. So we kind of see it's kind of the opposite of an exothermic reaction. We have all this thermal energy in our system that's then going to transfer that and allow that energy to be stored in the chemical bonds. Now, some kind of information about endothermic reactions and how we can identify them are that it's going to feel cool to the touch because we decrease the amount of thermal energy in our system. So it's going to feel cold to us. And this is where you're going to need your ice cube. So if you get your ice cube now, go ahead and go run and get that. Now that you have your ice cube, you put it in your hand and you feel that it's cold. And that's because the thermal energy is being absorbed by the ice cube. So if we're just focusing on the ice cube, we see that thermal energy is being absorbed from your hand. That's kind of where we'd start. And there's some chemical energy in the bonds and the way that the molecules are arranged. But really, you feel that it's cold because that energy is being taken out of your hand and absorbed into the system of the ice itself. But some other hallmarks of the endothermic reaction are the products have higher chemical energy than the reactants do. So it's kind of the exact opposite of the exothermic reaction. So we see that our chemical energy here in our reactants is kind of low. They're low. They don't have a lot of energy stored in them. But then once we form our new substances, they store a lot more chemical energy. And then in this case, the energy will show up as a reactant in the equation. So that video we watched, we reacted sulfur and iron, but we had to add some heat and energy to make this reaction happen so that we could form iron sulfide. And so again, the iron sulfide is going to store a lot more chemical energy than the iron and the sulfur did themselves. And we need some heat, we need some extra energy to be able to make this process happen. Now, so looking at the same chemical energy and reaction time or reaction progress chart that we looked at for an exothermic reaction, when we look at an endothermic reaction, so we're going to start with a little less energy with our reactants in this case. So kind of the slide before, the reactants have less energy than the products do in an endothermic reaction. So we get kind of a graph that, let me label this again. So here would be our reactants, R for reactants. And then as they go up, again, we have to kind of go up, and then we're going to come back down just a little bit. Again, that's that activation energy that we talked about. We'll focus more on that once we start looking at the actual numbers and how much chemical energy is and all those things. But again, our products over here are going to have a lot more energy than our reactants did. So we go up, and then we kind of will drop down just a little bit to get over this kind of activation energy. But you can see the products still have more chemical energy than the reactants did. And that's, again, what just the general shape that we would look at. Obviously, how much energy we will calculate and we'll look at later. But now just kind of focusing on the general shape and trend that we would see. And this is what our graph would show. So you have completed the video lesson. So go ahead and answer the six questions at the bottom of this Go Formative. Then you'll be good to go. And just remember that the multiple choice questions, they will light up green if you get them right. So just give it a second to refresh. The short answer questions, don't worry too much about those. I'll check those, but those won't show up as like right or wrong. It'll just stay a question mark out of 1.